Here's an example of a horizontal projectile. It's launched from a height of 10 metres with a horizontal velocity of 12 metres per second. We're not taking into account air resistance here. Now the path of the flight is a parabola, and each dot on the flight, that represents 0.1 of a second. The open circle here represents 1 full second. So the flight has gone on for about 1.4 seconds. And we can check this by using our special measure here. We just put it over the end of the flight and we can see that it's going to be 1.43 seconds. So the flight lasted 1.4 seconds to two significant figures. Let's analyse the motion of the cannonball by displaying its acceleration. As you can see, the acceleration vector is the same length throughout the flight, and it's pointing always vertically downwards. Now this implies a constant vertical acceleration acting on the cannonball. This vertical downward acceleration is due to the force of gravity. But as you can see, there is no horizontal acceleration taking place with the cannonball. There is no horizontal acceleration at all, but there is a constant vertical acceleration, which is due to the force of gravity acting on the cannonball. And that's what gives this cannonball its distinct path of a parabola. Now let's have a look at the velocity vector of the cannonball during its flight. As you can see, it's getting longer and its direction is more and more downwards. Its velocity is therefore increasing. Now a better way of analysing the motion of the cannonball is to break up that velocity vector into its respective horizontal and vertical components, because then we'll see what's happening vertically and then we'll see what's happening horizontally to the velocity of the cannonball. We're now looking at the cannonball's horizontal and vertical velocity components. The horizontal velocity component is constant during the flight. The vertical velocity component is changing during the flight. It's getting longer. Now this is because the vertical motion is subject to the acceleration of gravity, while there is no acceleration in the horizontal component. Here's a snapshot of the horizontal and vertical components of the cannonball's velocity taken at 0.5 seconds into the flight and 0.9 seconds into the flight. Now as you can see quite clearly, the horizontal velocity component is the same length at 0.9 seconds. And that tells us that the horizontal component of velocity does not change. It's not accelerating. But if you compare the vertical velocity at 0.5 seconds with the vertical velocity at 0.9 seconds, you definitely see that there's an increase in the length of the vector, which means it's accelerating downwards. And this acceleration is due to the force of gravity acting on the cannonball. So the important thing to note is this. Horizontal velocity is constant for a horizontal projectile, but its vertical velocity is changing, which means it's accelerating downwards. And the other key fact we have to remember, because the two components are at right angles to each other, is that the two motions are independent of each other. So we go to look at different types of problems involving projectiles, we'll note we can treat them in two different separate independent ways. We can look at the motion horizontally and we can look at the motion vertically, because both are independent of each other. Here's a snapshot of the horizontal and vertical velocity components at the times of flight shown. Now the aim here is to construct graphs of the vertical and horizontal velocity components. Now remember, a velocity time graph is all the vectors arranged along a timeline. It's as simple as that. Now we'll start with the horizontal component of the velocity. Now the convention is quite simple. The horizontal motion, if it's going towards the right, we'll consider that positive. So when it comes to portraying the vectors on a graph, we have to drag them over and then turn them on their side so that the tail is sitting on the timeline. Now once we arrange all the horizontal vector components on the timeline, we have a good idea of the shape of the horizontal velocity component of that particular motion. So let's start then. So we start at 0.2 seconds. That's our first snapshot. So we take the velocity vector and over here, and we just turn it upside down, or not upside down, on its side like that, and place it on the 0.2 second mark of the timeline. That's our first vector done. We do the same with the 0.5 second one. We take that over, we have to turn it on its end so as it's at 0.5 seconds like that. The 0.7 second one, we do the same, drag it away, turn it over and place it on the 0.5 second mark of the timeline. 1 second, the horizontal components, we drag that over like that and we place it like that, stack it like that, 1 second. The penultimate one at 1.2 seconds, we'll take that away and we will turn it over and put it on the graph at that, the 1.2 second mark. And the final one, which just lies along here, is maybe hard to see, at the end, just before the end of the flight, we take that over at 1.4 seconds, turn it this way and place it at 1.4 seconds. Now you can see quite clearly from that stack that the horizontal velocity vectors are not changing. In fact, it comes out to be about 12 meters per second if we actually see it. And that was the launch velocity. Horizontal launch velocity was 12 meters per second on that scale. But much more importantly, we can get a feel of the graph of the horizontal velocity components, because if we just draw a line right across all the tops of the arrows, you can see the line is definitely a straight line. And that is the graph for the horizontal velocity component. And the most important thing we've got to get from this is that the horizontal velocity does not change in a horizontal projectile. Now let's take a look at the vertical velocity components. I've taken away the horizontal components to make the diagram a little bit clearer. And we're going to do the exact same thing again. We're going to stack up all the velocity component vectors along the timeline and see what kind of shape of graph we get. Remember, the velocity time graph is just simply a whole lot of velocity vectors stacked up where we can see their outline. So in this particular case, we're still looking at a convention, this time in the vertical, that upwards is positive and downwards is negative, and we'll stick with that convention. So the velocity vectors are pointing downwards, so therefore our graph, we have to stack them tail on the timeline and they'll be pointing downwards. So we start off the same idea, we don't have to flip them this time. We drag over the 0.2 second velocity vector and we'll place it on the chart like that. Then we'll drag over the 0.5 second one and do the same. 0.7 seconds will go there in the timeline. And 1 second will go there in the timeline. And then we have got 1.2 seconds, stack up the vectors on the timeline, and finally 1.4, our final velocity will be like that. Now you can see that there's a difference in all the lengths of the vectors, and that means a very important thing. It means that the vectors are increasing in length downwards, which means they're accelerating downwards. Now the graph of that is found by just drawing a line from here. Presumably the initial velocity vector downwards is going to be 0. The initial velocity component vector is 0. So we draw a line down like that and we can see we're going to get a straight line all the way down like that. And that is the graph of the vertical velocity components. Now a very interesting thing we can do now is we can decide to work out the gradient of that graph, because if the gradient comes anywhere near the acceleration of gravity, then we have done a lot of studying on projectiles. Now that we've got our vertical velocity component graph drawn, all we have to do is work out the gradient of the graph. And the gradient of the graph is going to give us a value for the acceleration of the graph. So let's start off by putting down how we find the gradient of a straight line. The gradient is going to be equal to the change in the y coordinates divided by the change in the x coordinates. Now we'll match that up with our graph here. The change in the y coordinate corresponds to a change in the velocity, so that has to become delta v. And the change in the x coordinate, well, that's got to be change in time, delta t. So the gradient of that graph is going to be equal to the acceleration of the graph, a velocity time graph, which is simply equal to delta v over delta t. So let's work out what that is then. We look to see, first of all, we start at 0 here and we go along. We're going to hit something like here 1.5. So that's going to be 1.5 here of a change in the time. So we'll put that in blue here. So it's going to be 1.5 seconds. And we'll draw another line. And that's going from here all the way down to this point here, make it easy for ourselves. And that's going to be minus 15 meters per second. So we'll draw that blue up here. And it's minus because it's down the way, minus 15 meters per second. Now, doing that calculation, we end up with a value of minus 10 meters per second every second. So the gradient of that graph, in fact, is almost equal to the acceleration due to the force of gravity. The accurate figure is 9.8 meters per second every second. So we've done not bad from a simulation to give us that the velocity graph. When we convert it into the gradient gives us the acceleration, and acceleration is the acceleration due to gravity. So let's recap what we've done in this lesson. We've done the following most important things. We have drawn two graphs. We've examined the motion of a horizontal projectile. To make it simple for ourselves, we have looked at the components of the velocity of the object, the cannonball, as it goes through time. And we found out a very important thing, that the horizontal component of the projectile's velocity does not change. It remains constant. And we can put that down like that. The horizontal component of a horizontal projectile of its velocity remains the same, it's constant. But the vertical component of the projectile's velocity, once we draw that out, is going to be accelerating downwards with the acceleration due to the force of gravity. Now there's two graphs which sum up the components, the velocity components of a horizontal component and the vertical component of a horizontally projected cannonball. Two important graphs.